In this video, we're going to discuss integral domains. Alright, now we get to an interesting concept in ring theory called a zero divisor. Suppose R is a ring, let R be a non-zero element of R, and we say R is a zero divisor if you can find some other element in R such that when you multiply them together, you get 0. So obviously this looks very weird at first because in the rings we're used to working with from other math courses, there are no zero divisors. So let's look at an example where there is one. Let's look at z mod 12z. If you multiply 4 times 3, you get 12, but 12 mod 12 is 0. So 4 is a zero divisor because you multiplied two non-zero things together and you got 0. And in fact, in general, for z mod nz, if you take a divisor, non-trivial divisor of n, then it is a zero divisor. Namely, right, n is q times d, then you can see q bar times d bar is n bar, which is 0. So, and z mod nz, when n is not a prime, there are definitely going to be zero divisors for every single divisor of n. In fact, if the GCD of k and n is not 1, then k bar is a zero divisor. It's not too hard to prove. You just take the Bezout coefficients, right, that you know that if d is the GCD, then you know that d is a multiple of k and n, which means r bar times k bar is equal to d bar minus Sn, which is 0 mod n. But at this case, d has to divide n, so that actually gives you what you need. You just go back up here and say, well, if I multiply by a right multiple of q, I'm going to get 0. And you just have to prove that q times r is not 0. So certain types of rings have lots of zero divisors. We usually actually prefer not to have them. What is the big point behind having them? Well, let R be a ring, and suppose you have something that is not a zero divisor, then the left cancellation law holds that B and C be in R, then AB equals AC implies B equals C. Why is that true? Well, if AB equals AC, then if you subtract AC from both sides, you get ABC minus AC equals 0. You can factor out the common factor of A. Then you have to conclude one of these two has to be 0. Why? Because if neither of them are 0, then congratulations, you've got two non-zero things that multiply to get 0. That would imply that A is in fact a zero divisor. Which is a contradiction. So it follows that since A is not a zero divisor, one of these two has to be 0. We're also assuming A is not 0, so B minus C has to be 0, which means B equals C. In fact, if A is a zero divisor, then the opposite ends up being true. You actually can find a B and a C with B not equal to C and AB equals AC. The most obvious choice is to just take B to be something such that A times B is equal to 0. Since A is a zero divisor, this should be possible. And then just take C to be 0 itself, because then AB and AC are both equal to 0, so they're equal to each other. But B is not equal to C. So we like our rings to not have zero divisors, because when you don't have a zero divisor, you can cancel. If you do have a zero divisor, you can't. So this is a bit beyond the scope of the course, but to point out why this is important, a common problem you've had to deal with a lot in mathematics, in lower level mathematics, is solve a function equals 0, say a polynomial, that's the most common one. but trig functions also come to mind. A common strategy you often had to do was that you would factor your expression into two factors, and then you'd remember that you could break your problem up into two subproblems. If this expression were equal to 0, then either the first factor is 0 or the second factor is 0. This assumes no zero divisors in order to work. Once you're working in a setting of a function who's taking values in a ring that has zero divisors, this technique fails to work. And in fact, you can get all kinds of weird things. So for instance, when you're studying polynomials, one of the things you use this for is to prove that the number of roots to a polynomial is at most its degree. And the proof is by induction. If you can factor a polynomial, its factors have smaller degree. The roots of the polynomial have to be the unions of the roots of the factors. If you're working with a polynomial over a ring with zero divisors, that's no longer true because of this nonsense. The simplest example is to look at f of x equals 2x and z mod 2z. As a linear function, you would expect it to only have one solution to the equation 2x equals 0. Unfortunately, there are two solutions. There's 0 bar and 2 bar. Because you can check that 2 bar times 2 is in fact 0. So your intuition betrays you, and the theorems that we learned in grade school no longer work. You have more solutions than you have degree. And that's because this ring has zero divisors. So that with that in mind, that tells us why we like this definition, an integral domain. So a commutative ring with unity. So unity, we'll explain what that is in a moment. It's called an integral domain if it has no zero divisors. So that's that nice setting where the cancellation property works. If you're working with functions with values in an integral domain, solving equations by factoring is an actual viable strategy. A unity is just the multiplicative identity. And it's usually denoted 1 instead of e. I call it integral domain because you're really supposed to think of things like the integers. Another example is called the Gaussian integers due to Gauss, which is numbers of the form a plus bi, where a and b are integers. So the claim is that this is a commutative ring with unity, and it has no zero divisors. Well, let's prove it has no zero divisors. That's actually going to take some work. So take a non-zero Gaussian integer and suppose x times y equals 0 for some other Gaussian integer. What do I need to prove? I need to prove that y is actually 0. That would allow me to conclude that x is not a zero divisor, and since x was an arbitrary non-zero element, that would allow me to conclude that there are no zero divisors. So write x and y as real plus imaginary parts. What is x times y? By our formulas, it's ac minus bd plus ad plus bc times I. On the other hand, if we want x times y to be equal to 0, then it has to be 0 plus 0i. We've got a real part. We've got imaginary parts. They have to be equal. So we see AC minus BD has to be 0, and AD plus BC has to be 0. So this is what we have so far. We've created a system of linear equations. If you multiply the second equation by b, you get ABD plus b squared c equals 0. You have, from here, it's worth pointing out we have that AC is equal to BD. So I can replace the BD with AC and I get a squared c plus b squared c is equal to 0. I can factor out the common factor of c, and I have this expression. Now if x is non-zero, that implies that a squared plus b squared is not 0. Why? Because it can't be the case that both a and b are 0, so at least one of them is not 0. That means one of these squares, possibly both of them, have to be a positive number. So this sum has to be positive. So this product is 0, this number is not. It follows that c is equal to 0. Congratulations, the real part of y is 0. Now I do the same thing. I multiply equation 2 again, this time by a. I get a squared d plus acb, or abc, equals 0. Now I substitute and replace ac with bd. I factor out the common factor of d, and now I conclude that d is equal to 0. So from these two equations, I discover that the real and imaginary part of y are both 0, so y is actually 0 itself. So x is not a zero divisor. The Gaussian integers have no zero divisors. Of course, the other step I need to point out is that the Gaussian integers are in fact a commutative ring with unity. That's a simple calculation. You multiply two of them together in either order, and you see that the only difference between the middle two terms has to do with commuting. And so, in fact, and we know multiplication of integers is commutative. So, in fact, multiplication is commutative for Gaussian integers. And the unit is just 1 plus 0i. And you can check that when you do the multiplication out. So there was an example of an integral domain. Now we get to our theorem. An equivalent definition of integral domains is that the cancellation property always holds. So this one is in the textbook, although our version of the proof is going to be shorter because I proved the cancellation property for a given non-zero divisor separately. So let R be a commutative ring with 1, then it's an integral domain if and only if for every non-zero element and any pair of elements the cancellation law holds. So let R be an integral domain, let A be a non-zero number, then A is not a zero divisor because you're an integral domain. Then it follows from the fact we proved earlier that the cancellation law holds, because we already proved it earlier. So that implies this result. Now we just need to show the other direction. And how are we going to do the other direction? Well, suppose R is not an integral domain. Then let A be a zero divisor. And then take our bad example. Let B be a non-zero number such that A times B is 0. Then AB is equal to A times 0, but B is not 0. So if you're not an integral domain, there actually exists an A in R take away 0, and a B and a C such that AB equals AC and B is not equal to C. So, and that's a good exercise in logic, that the negation of this statement is, in fact, there exists an A and R take away 0, B and C and R, such that AB is equal to AC and B is not equal to C, which is exactly what we showed.